What is the temperature at which we get the same reading on both Celsius and Fahrenheit scales? The options given are 40 degrees Celsius, minus 40 degrees Celsius, 20 degrees Celsius and minus 20 degrees Celsius. Now, let's assume that T is the required temperature at which we get both the readings same for both these scales. So, if T is the temperature, so on Celsius scale, we can write T minus 0 upon 100 minus 0 is equals to T minus 32 upon 212 minus 32, where 0 and 100 are the boiling and freezing and boiling points of water in degrees Celsius, and 32 and 212 are again freezing and boiling points of water in Fahrenheit scale. So T upon 100 equals T minus 32 upon 180. So on solving this, we get the value of T is equals to minus 40. Now this is minus 40 degrees Celsius, hence option B is the correct answer. For any given scale x, the ice point is 40 degrees and the steam point is 120 degrees. For another scale y, the ice point and steam point are minus 30 and 130 respectively. If x reads 50 degrees, then y would read, the options given are minus 5 degree, minus 8 degree, minus 10 degree and minus 12 degrees. Now, in general, the relation between any two scales can be found out as the temperature in that scale. So for this, let's say Tx minus the freezing point upon the difference between the freezing and the boiling point in that scale. So we can say delta of boiling and freezing. So this would be equal to, for the next scale, that is y scale, same Ty and freezing point upon delta boiling and freezing. So similarly, now for the x scale, the ice point is given as 40, whereas 40, and the steam point is given as 120. So 120 minus 40 is equals to Ty is what we need to find out. X reads 50, so the Tx over here would be 50. Ty is what we need to find out. For another scale y, ice point is minus 30, so minus of minus 30 will become plus 30 upon the difference between the boiling and freezing point is 130 minus 30, so that becomes total of 160. So therefore, solving this, we get the value of Ty as minus 10 degrees. So hence option C is the correct answer. The length of a metal rod at 15 degrees Celsius is 50 centimeters and at 90 degrees Celsius it is 50.15 centimeters. The coefficient of linear expansion of the material of rod is, the options given are 4 into 10 raised to minus 6 per degree Celsius, 2.4 into 10 raised to minus 6 per degree Celsius, 4.2 into 10 raised to minus 5 per degree Celsius and 4 into 10 raised to minus 5 per degree Celsius. Now for linear expansion, we know the formula. Final length L2 is equals to L1, that is the initial length, times 1 plus alpha into delta T, where delta T is nothing but the change in temperature and alpha is the coefficient of linear expansion. So the L2 or final length is 50.15, so 50.15 is equals to L1, that is 50 centimeters, to 1 plus alpha is what we need to find out, and delta T is the difference between the temperatures, that is 90 degrees Celsius minus 15 degrees Celsius, so that would be 75 degrees Celsius. So to solve this, we get 1 plus alpha times 75 is equals to 50.15 upon 50 So 75 times alpha is equals to 50.15 minus 50 upon 50. So alpha is equals to 0.15 upon 50 into 75. So this again comes out as, let's say, 10 raised to minus 2, 15 5s are 75. So this is 1 upon 250 into 10 raised to minus 2. So this comes out as 4 into 10 raised to minus 5. So 4 into 10 raised to minus 5 is the answer. Hence, option number D is the correct answer. The value of coefficient of volume expansion of glycerin is 5 into 10 raised to minus 4 per Kelvin. The fractional change in the density of glycerin for a rise of 40 degrees Celsius in its temperature is, the options given are 0.01, 0.015, 0.02 and 0.025. Now basically we need to see that density is nothing but mass upon volume. So therefore volume we can write it as mass upon the density rho. So also we know that for volume change, the volume V2 can be given as V1 times 1 plus gamma into delta T, where delta T is the change in temperature and gamma is the coefficient of volume expansion. So by substituting volume as mass by density, so we get mass upon density for the second case is equals to mass upon density in the first case to 1 plus gamma times delta T. These mass terms gets cancelled out because there is no addition of mass, only the volume changes and hence the density is changing. So therefore rho 2 can be given as rho 1 times 1 plus gamma into delta T. Now fractional change is nothing but gamma 1 minus gamma 2 upon gamma 1. Pardon me, rho 1 minus rho 2 upon rho 1. So that is nothing but 1 minus rho 2 upon rho 1. So this is nothing but rho 2 upon rho 1 is 1 minus 1 upon 1 plus gamma into delta T. So that is 1 minus 1 plus gamma times delta T raised to minus 1. Now for this, in order to simplify this, we will use the binomial expansion. So 1 minus, what we end up with is 1 minus gamma times delta T. As you know, binomial expansion for 1 plus x raised to n is nc0 plus nc1 x raised to 1 plus nc2 x raised to 2 and so on. So since the value of gamma is 10 raised to minus 4, so when it goes into the square term, it would go 10 raised to minus 8 and that can be neglected. So we take only the first term. So now this expression is simplified as gamma times delta T with this 1 and 1 gone. So gamma, substituting the value as 5 into 10 raised to minus 4 into delta T, or change in temperature, is 40 degrees Celsius. Here the expansion is given in Kelvin, whereas the change in temperature is given in degrees Celsius. However, since the change in degrees Celsius and Kelvin is the same, like 1 degree rise in temperature in the degrees Celsius scale is same as 1 degree rise in the Kelvin scale, so we can directly substitute here as degrees Celsius. So this comes out as 0.020, hence option C is the correct answer. The density of mercury at 0 degrees Celsius is 13,600 kg per meter cube, and volume coefficient of expansion of mercury is 1.82 into 10 raised to minus 4 per degree Celsius. The density of mercury at 50 degrees Celsius is nearly the options given are 13,333 kg per meter square, 13,477 kg per meter square, 13,733 kg per meter cube, and 13,900 kg per meter cube. Now, as we've seen in the previous formula, density rho2 is equals to rho1 times 1 plus gamma into delta T. So using this same formula again from the previous sum, so substituting the values, density initially is 13,600 upon 1 plus gamma is given as 1.82 into 10 raised to minus 4, so 1.82 into 10 raised to minus 4, and the delta T is change in temperature, so 50 degrees minus 0 degrees, so that is again 50. So therefore the value of rho2 that we get is 13,477.35 kg per meter cube. So the closest answer is 13,477, hence option B is the correct answer. Which of the following substance A, B and C has the highest specific heat? The options given are A, B, C, and all have equal specific heat. Now let's look at the formula for heat content. Q is equals to mc delta theta, where delta theta is the change in temperature. So let's say dq, and let's just differentiate this. So dq by dt with respect to time is equals to mc. C is the specific heat and that is constant. Mass is also constant, so d theta by dt. Now from this relation, d theta by dt is nothing but dq by dt into 1 by m into c. As we can see, d theta by dt is nothing but the change in temperature with respect to time, and it is inversely proportional to the specific heat C. So dq by d theta by dt is inversely proportional to the specific heat, which means that higher would be the change in temperature with respect to time, lower would be the specific heat. So basically for graph A, as we can see, for a small change in time, the change in specific heat or the temperature is very large, and this keeps on decreasing for the various as we go for graph B, and for graph C it is the least. So say from time t1 to time t2, the change in heat or change in temperature is just this much value, whereas for B it is a little higher value, and for A it is much higher. So for C, since d theta by dt is small, so the graph C has the highest specific heat, hence option C is the correct answer. For helium, gamma is equals to 5 by 3. For oxygen, gamma is equal to 7 by 5. The value of gamma for a mixture consisting of 1 mole of each gas will be, the options given are 3, 1.5, 2.5 and none of these. Now the number of moles of oxygen is equals to number of moles of helium, which is 1, and gamma for helium is given as 5 by 3, whereas that of oxygen is given as 7 by 5. So for the mixture we can find out the value of gamma as the total number of moles in the mixture, that is nothing but NO plus N helium upon gamma minus 1. This is of the mixture, and it equals to the sum of individual components. So number of moles of oxygen upon gamma of oxygen minus 1 plus number of moles of helium upon gamma of helium minus 1. So therefore this n is equals to 1, so 1 plus 1, 2 upon gamma minus 1 is equals to 1 upon 5 by 7 by 5, 7 by 5 minus 1 plus 1 upon 5 by 3 minus 1. So that we get as 5 by 2 plus 3 by 2. So 2 upon gamma minus 1 is equals to 4. So gamma we solve it to get the value of 1.5. Hence option B is the correct answer. A 10-watt electric heater is used to heat a container filled with 0.5 kg of water. It is found that the temperature of water and the container rises by 3 Kelvin in 15 minutes. The container is then emptied, dried and filled with 2 kg of oil. The same heater now raises the temperature of container oil system by 2 Kelvin in 20 minutes. Assuming that there is no heat loss in the process and the specific heat of water is 4200 joule per kg per Kelvin, the specific heat of oil in the same unit is equal to, the options given are 1.5 into 10 raised to 3, 2.55 into 10 raised to 3, 3 into 10 raised to 3 and 5.1 into 10 raised to 3. Now let's look at the oil. Basically what we need to use here is the Q, or energy supplied, is equals to MC delta T. This would be for oil plus mass of oil, specific heat of oil plus change in temperature, plus it is also absorbed, the heat given by the heater is also absorbed by the container. So mass of container, specific heat of container in 10 delta T, that is the change in temperature of the container. So therefore the electric heater is given in terms of watt. This is the unit of power, and here is the energy. So power is nothing but energy done per unit time. So energy would be power into time. So that is 10 into time is, for oil is 20 minutes. So into 60 would give it in terms of seconds, is equals to mass of oil is given as 2 kg. Specific heat of oil is what we need to find out, and the temperature rises by 2 Kelvin, so delta T is 2, plus mass of container is unknown, specific heat of container is also unknown, and delta T is again 2. So from this let's just keep it this way because we have unknown over here also. So in order to find out MC times Cc, let us consider the case of water. Applying the similar formula, but instead of oil, using the notations for water, we get 10 watt into 15 minutes into 60 seconds is equals to mass of water is given as half kg or 0.5 kg, and specific heat of water is given as 4200 joule per kg per Kelvin, and temperature rise is 3 Kelvin, plus MC Cc into temperature rise now is 3. So from this equation we get the value of MC times Cc to be 900. Now substituting MC times Cc as 900 in this, so we get 10 into 20 into 60 is equals to 4 times C of oil plus 900 into 2. So that is 12,000 is equals to 4 times C of oil plus 1,800. So solving for C of oil, we get the value of C of oil as 2.55 into 10 raised to 3 joule per kg per Kelvin. Hence option B is the correct answer. Same quantity of ice is filled in each of the two metal containers P and Q having the same size, shape and wall thickness but made of different materials. The containers are kept in identical surroundings. The ice in P melts completely in time T1 whereas that in Q takes a time T2. The ratio of thermal conductivities of the materials of P and Q is, the options given are 2 is to T2 is to T1, T1 is to T2, T1 square is to T2 square, and T2 square is to T1 square. Now the formula for heat Q is given as Ka d theta by dt d theta by dx times T. So where T is the time, K is the thermal conductivity, A is the area, and d theta by dx is the change in temperature per unit length. So from this expression, by rearranging the terms, we can see that K is inversely proportional to the time T. So therefore K1 upon K2, that can be said as Kp upon K of Q is nothing but T2 upon T1. Hence option A is the correct answer. If two metallic plates of equal thickness and thermal conductivities K1 and K2 are put together face to face and a common plate is constructed, then the equivalent thermal conductivity of this plate will be, the options given are K1 K2 upon K1 plus K2, 2 times K1 K2 upon K1 plus K2, K1 square plus K2 square raised to 3 by 2 upon K1 K2, K1 square plus K2 square upon 2 times K1 K2, the whole thing raised to 3 by 2. Now let's look at the schematic. Suppose this is one plate having thickness, let's say L, and area of cross section A. This is fused with another plate which also has a thickness, let's call it L again, and A is the area of cross section. Now these both plates together give a series combination. So in series, the resistance, equivalent resistance or thermal resistance, is addition of individual resistances. So R equivalent is equals to R1 plus R2, and the resistance, thermal resistance, can be written in terms of conductivity as 2 times L upon K equivalent into area, which equals to L upon K1 into A plus L upon K2 into A. So therefore 2 upon K equivalent is equals to 1 by K1 plus 1 by K2. So solving this, the value of K equivalent, we get it as 2 times K1 K2 upon K1 plus K2. Hence option B is the correct answer. The ratio of diameters of two metallic rods of the same material is 2:1, and their lengths are in the ratios 1:4. If the temperature difference between their ends are equal, the rate of flow of heat in them will be in the ratio. The options given are 2:1, 4:1, 8:1, and 16:1. Now the heat flow Q is given by Ka delta theta upon L times the T. So therefore let's simplify this relation. Q by T, or the rate of heat flow, is now proportional to, K is a constant, so it is proportional to A by L, since the temperature between both the ends are also kept fixed. So this Q by T is proportional to A by L, and A can be considered as pi r square, so that is r square upon L. So Q by T is basically proportional to r square upon L. So Q by T for the first case upon Q by T for the second case would be R1 upon R2 the whole square into L2 upon L1. So the radiuses are in the ratio 2:1. So since diameters are in the ratio 2:1, radiuses also would be in the ratio 2:1. So 2:1 square into lengths are given in the ratio 1:4. So 1:4 this comes out as 4 times 4, that is 16. So Q by T, the first case, is equals to 16 times Q by T for the second case. Hence option D, 16:1, is the correct answer. A wall has two layers A and B made from different materials. The thickness of both the layers is the same. The thermal conductivities of A and B are Ka and Kb such that Ka is equals to 3 times Kb. The temperature across the wall is 20 degrees Celsius. In equilibrium condition, the options given are: the temperature difference across A is 15 degrees Celsius. The temperature difference across A is 5 degrees Celsius. Temperature difference across A is 10 degrees Celsius, and the rate of transfer of heat through A is more than that through B. Let's draw the schematic. So suppose this is a wall of material A and this is another wall of material B. Since both the thicknesses are the same, so conductivity of A, and let Kb be the conductivity of wall B. Let theta 1 be the temperature at this face, theta be the temperature at the interface of both the walls, and theta 2, let it be the temperature at the end face of wall B. Now since this is a series flow, so therefore the rate of heat flow is the same. So option D is negated. So rate of heat flow is the same, and hence option D is negated. So now substituting the formula for rate of heat flow, so Ka times the area of cross section into delta theta, that is theta 1 minus theta, per unit length of the wall, let's consider L is the thickness of the wall, is equals to Kb times area of wall B, theta minus theta 1 upon, again the thickness is the same, so L. So instead of Kb, let's put 3 times, instead of Ka, let's put 3 times Kb. So 3 Kb times theta 1 minus theta is equals to Kb times theta minus theta 2. So these get cancelled out. So what we are left with is 3 times theta 1 minus 3 theta is equals to theta minus theta 2. So therefore 4 times theta 1 minus 4 times theta is equals to theta 1 minus theta 2. We are just adding theta 1 on both sides. So 4 times theta 1 minus theta is equals to theta 1 minus theta 2. Now the temperature between difference across the wall, that is theta 1 minus theta 2, is given as 20 degrees Celsius. So 4 times theta 1 minus theta is equals to 20. So theta 1 minus theta is the temperature difference across the wall A. So theta 1 minus theta is 20 upon 4, that is 5 degrees Celsius. Hence option B, temperature difference across A is 5 degrees Celsius. That's the correct answer. Given that P joule of heat is incident on a body and out of it Q joule is reflected and transmitted by it, the absorption coefficient of the body is, the options given are P by Q, Q by P, Q minus P by P, and P minus Q by P. Now let the total heat that is incident Q is equals to, that is given as P, and Q is given as the amount of heat that has been reflected and as well as transmitted. So Q joules of heat is reflected and transmitted. Now we know that the total heat is distributed into 3 forms, that is absorbed plus heat reflected plus heat that is transmitted. So therefore Q is equals to heat absorbed plus QR and QT, let's write it as small q. So therefore P is equals to QA plus small q, and therefore QA, or amount of heat absorbed, is equals to P minus Q. Now coefficient of absorption is nothing but A, which is QA upon total incident heat. So QA can be written as P minus Q, and total incident heat is P. Hence option D, P minus Q upon P, is the correct answer. If a block is kept at equal distance from three bulbs of same surface area for equal time, if A emits red color, B emits blue color, while C emits yellow color, which face of the block will get heated the most? The options given are facing A, facing B, facing C, and facing D. Now, as we know from Wien's displacement law, lambda, or the wavelength, is inversely proportional to the temperature. Now, in a spectrum of light, that is VIB, GY, OR, out of these colors, this is the increasing order of wavelength. This is the increasing order of the frequency, and this is the increasing order of the wavelength. So as we can see, blue has the shortest wavelength, after which comes yellow, and the highest or longest wavelength is emitted by the red color. Now according to this and this relation, so we can say that the temperature emitted by the blue light would be greater than temperature of yellow light as compared to that of red light. So therefore, since temperature of blue light is the highest, so therefore side facing the blue color, that is B, would be the highest temperature. Hence option B is the correct answer. Wien's constant is 2892 into 10 raised to minus 6 SI unit, and the value for lambda max for moon is 14.46 micron. The temperature of moon is, the options given are 200 Kelvin, 2000 Kelvin, 20 Kelvin, and 200 degrees Celsius. Now from Wien's displacement law, the formula is temperature is proportional to the inversely proportional to the wavelength, or the maximum wavelength. So this proportionality constant is removed by introducing the Wien's constant. So T is equals to B upon lambda max, where B is the Wien's constant. So now T is equals to, the value of B is given as 2892 into 10 raised to minus 6 upon the lambda max value is given as 14.46 micron, that is 10 raised to minus 6. So this comes around 200 Kelvin. Hence option A, 200 Kelvin, is the correct answer. A sphere at 600 Kelvin is losing heat due to radiation. At this temperature, its rate of cooling is R. The rate of cooling of the sphere at 400 Kelvin is, the temperature of surrounding is 200 Kelvin. The options given are 3 by 16 R, 8 by 27 R, 16 by 3 R, and 7 R. So the rate of cooling R, that is nothing but delta Q upon delta T, can be given by Stephen-Boltzmann's law, that is A E sigma into T1 raised to 4 minus T0 raised to 4, where T1 is the temperature of the body and T0 is the temperature of the surrounding. So for the first case, R1, R as given would be A E sigma into, the temperature is given as 600, so 600 raised to 4 minus 200 raised to 4. And let's consider for the second case, R dash would again be A E sigma, since the material and the substance or the object isn't changing, So only change would be the temperature, and now it is 400 Kelvin. So 400 raised to 4 minus 200 raised to 4. Let's take a ratio of R dash and R. So R dash upon R would be 400 raised to 4 minus 200 raised to 4 upon 600 raised to 4 minus again 200 raised to 4. So by solving this, we get the value as 3 by 16. So therefore R dash is equals to 3 by 16 times R. Hence option A is the correct answer. Certain quantity of water cools from 70 degrees to 60 degrees Celsius in the first 5 minutes and to 54 degrees Celsius in the next 5 minutes. The temperature of the surrounding is, the options given are 45 degrees Celsius, 20 degrees Celsius, 42 degrees Celsius and 10 degrees Celsius. To solve this sum, we will need to use the Newton's law of cooling. So Newton's law of cooling basically says that the change in temperature theta1 minus theta2 per unit change in time is equals to K times Newton's cooling constant, the average temperature between the two states, so that is theta1 plus theta2 upon 2 minus temperature of the surrounding, that is theta naught. So according to this formula, let's substitute for the first case. So from 70 to 60 degrees Celsius, so 70 minus 60 in 5 minutes is equals to K times the average of 70 and 60. So 70 plus 60 upon 2 minus temperature of the surrounding is unknown, theta naught. So 70 minus 60 is 10, 10 by 5 is 2. 2 is equals to K times 70 plus 60 upon 2 is 65 minus theta naught. So let this be equation 1. Now for second case, the temperature would be 60 minus 54. Again for 5 minutes is equals to K times the average of 60 plus 54 minus theta naught, that is the temperature of surrounding. So 60 minus 54 is 6 by 5 is equals to K times the average value is 57 minus theta naught. So this is equation 2. So dividing equation 1 by 2, we get 5 upon 3 is equals to 65 minus theta naught upon 57 minus theta naught. So therefore 285 minus 5 times theta naught is equals to 195 minus 3 times theta naught. So solving this, 2 times theta naught is equals to 90. So therefore theta naught would be 90 by 2, that is 45 degrees Celsius. Hence option A is the correct answer. If the temperature of a hot body is increased by 50%, then the increase in the quantity of emitted heat radiation will be, the options given are 125%, 200%, 300% and 400%. Now from Stephen's law, we know that Q, or the energy, is proportional to the fourth power of the temperature. So therefore Q1 upon Q2 is equals to T1 upon T2, the whole thing raised to 4. So therefore Q1 upon Q2 is equals to, the temperature is increased by 50%. So let's say T1 is equals to T, and therefore T2 would be T plus T by 2 is raised to 4. So now solving this part, we get Q1 upon Q2 as 16 upon 81. So therefore Q2 is equals to 81 upon 16 times Q1. Now the percentage increase. For percentage increase, we'll need to solve Q2 minus Q1 upon Q1 times 100. The value of Q2, let's substitute as 81 by 16. So 81 by 16 times Q1 minus Q1 upon Q1 into 100. Taking out Q1 common and cancelling out. So 81 upon 16 minus 1 into 100. So solving this, we get the value as, which is approximately equal to 400%. Hence option D is the correct answer. A body cools at the rate of 0.6 degrees Celsius per second when it is 40 degrees Celsius above the surroundings. The rate of cooling when it is at 20 degrees Celsius above the same surrounding will be, the options given are 0.2 degrees Celsius per second, 0.3 degrees Celsius per second, 0.15 degrees Celsius per second, and 0.4 degrees Celsius per second. Now, according to Newton's law of cooling, so the change in temperature d theta by dt for the first case is equals to k times T minus T naught. So for the first case, d theta by dt is k times the temperature difference is given as 40 degrees, and the d theta by t1 dt is given as 0.6. So 0.6 is equals to k times 40. Let's this be equation 1. Now for the second case, d theta by dt, second case is equals to k times the temperature difference is now given as 20 degrees Celsius. So let this be equation 2. Dividing these two equations, you get 0.6 upon d theta by dt for the second case is equals to 40 upon 20. So this is 2. So d theta by dt for the second case is 0.6 upon 2, which is nothing but 0.3. Hence option C, 0.3 degrees Celsius per second, is the correct answer. If a body cools down from 80 degrees Celsius to 60 degrees Celsius in 10 minutes when the temperature of the surrounding is 30 degrees Celsius, then the temperature of the body after next 10 minutes will be, the options given are 50 degrees Celsius, 48 degrees Celsius, 30 degrees Celsius and 52 degrees Celsius. Now using the Newton's law of cooling, so change in temperature in the first case is 80 minus 60 and the time taken for it is 10 minutes is equals to the Newton's constant times the average temperature of 80 and 60, it will be 70 minus the room temperature or surrounding temperature is 30 degrees Celsius. So solving this, we get the value of K as 1 by 20. Now substituting this value or using this value of K for the second case, so 60 minus the final temperature that we need to find out. So 60 minus theta upon 10 minutes would be equal to 1 by 20 times the average of the two temperatures, that is 60 plus theta upon 2 minus surrounding temperature is 30. So this comes out as 1 by 20 times this 60 by 2 becomes 30 and gets cancelled with this 30. So we are left with theta by 2. So 60 minus theta upon 10 is equals to 1 by 20 times theta minus 2. So 60 minus theta is equals to theta by 4. So therefore 240 minus 4 theta is equals to theta. 5 theta is equals to 240. So therefore the value of theta is equals to 48 degrees Celsius. Hence option B is the correct answer. A clock which keeps correct time at 20 degrees Celsius is subjected to 40 degrees Celsius if coefficient of linear expansion of the pendulum is 12 into 10 raised to minus 6 per degree Celsius. How much will it gain or lose in time? The options given are 5 seconds per day, 10.3 seconds per day, 20.6 seconds per day and 20 minutes per day. Now, as we know, the time period of a pendulum is root of L by G. So time period is proportional to root of L. So therefore, time period of the second case divided by time period of the first case is nothing but root of L2 by L1. And L2 is the length of the pendulum after it has been subjected to 40 degrees Celsius. So using linear expansion, L2 is equals to L1 times 1 plus alpha into delta T, where delta T is the change in temperature and alpha is the coefficient of linear expansion. So therefore L1 gets cancelled. So what we are left with is 1 plus alpha is given as 12 into 10 raised to minus 6 times change in temperature. There is 40 minus 20, so that is 20. This is under the root. So the value of this comes out around 1.00011199. So in order to find out the deviation from the correct time, deviation would be equals to T2 minus T1 upon T1. So that would be, and this value is 0.00011199. So this is the amount of time that is changed per day. So let us convert it into seconds. So that would be 0.00011199 times 24 hours into 60 minutes into 60 seconds. So that we get as 10.37 seconds per day. Hence option B, 10.3 seconds per day, is the correct answer. In this, as the time period is proportional to the length, and since length is increasing, so the clock would basically count longer times and hence it would be losing time. Equal masses of two substances of density ρ1 and ρ2 are mixed together. The density of the mixture would be, the options given are half of ρ1 plus ρ2, root of ρ1 ρ2, ρ1 ρ2 upon ρ1 plus ρ2, and the last option is 2 times ρ1 ρ2 upon ρ1 plus ρ2. Now the density of the mixture, rho mixture, would be nothing but total mass upon total volume of the mixture. So let us consider mass of each substance as m, and since both these masses are equal, so mass of both the substances will be m, and the volume is nothing but mass upon density. So therefore density of the mixture is equals to total mass would be m plus m upon total volume would be volume of the first substance, that is m upon ρ1, plus volume of the second substance, that is m upon ρ2. So solving this, we get the value as 2 times ρ1 ρ2 upon ρ1 plus ρ2. Hence option D is the correct answer. The density of a substance at 100 degrees Celsius is 7.25 gram per cubic centimeters, and at 0 degrees Celsius is 7.5 grams per cubic centimeter. Coefficient of linear expansion is, the options given are 111 into 10 raised to minus 6 per degree Celsius, 111 into 10 raised to minus 5 per degree Celsius, 111 into 10 raised to minus 4 per degree Celsius, and 111 into 10 raised to minus 3 per degree Celsius. As we've seen in a previous formula, the ρ2 is equals to ρ1 upon 1 plus gamma times delta T. This equation has already been simplified in a previous formula, so let's use this again. So ρ2 is 7.25, which is equals to ρ1 is 7.5 upon 1 plus gamma times delta T is 0, 100 minus 0, that is 100. So solving this, 7.25 times 7 plus 7.25 gamma into 100 is equal to 7.5. So therefore 7.25 gamma into 100 is equals to 7.5 minus 7.25, which is 0.25. So gamma is equals to 0.25 upon 100 into 7.25. So this value comes around 111, and let's look at the powers. So if we see, it comes around 10 raised to minus 6, or pardon me, it comes to 10 raised to minus 4. This value, when we solve it, it comes to 3.33 into 10 raised to minus 4. But the relation between coefficient of linear expansion, area expansion and volume expansion are such that alpha is equals to beta by 2, which equals to gamma by 3. So therefore, and this is the value of gamma, so therefore alpha is equals to gamma by 3, so that is 3.33 into 10 raised to minus 4 upon 3. So this value comes around 111 into 10 raised to minus 6 per degree Celsius. Hence option A is the correct answer. A room at 20 degrees Celsius is heated by a heater of resistance 20 ohms connected to 200 volts mains. The temperature is uniform throughout the room and heat is transmitted through a glass window of area 1 meter square and thickness 0.2 centimeters. Calculate the temperature outside. The thermal conductivity for glass is given as 0.2 calories per meter degrees Celsius, and the value of 1 calorie is 4.2 joules. So the options given are 1.524 degrees Celsius, 15.24 degrees Celsius, 20 degrees Celsius and 10 degrees Celsius. Now let's assume that theta is the outside temperature. So therefore, the rate of heat flow from the room to outside, dq by d theta or dq by dt is Ka, the change in temperature theta 1 minus theta 2 upon the thickness of the glass. So K is given as 0.2, area of 1 meter square, the inside temperature is 20 and outside temperature we don't know, and L is 0.2 centimeters, so 10 raised to minus 2 in order to convert it into meters. So this value dq by dt comes around 100 into 20 minus theta, this is calories per second. Now the heat that is produced by the heater is nothing but V square upon 4.2 R. So V square is 200 squared upon 4.2 into R is resistance of 20 ohms. So this value we obtained in calories, which is close to around 476.2 calories per second. So by equating these two equations, we get 100 times 20 minus theta is equals to 476.2. So therefore, solving for value of theta value comes around 15.24 degrees Celsius. Hence option B is the correct answer. A hollow sphere of mass m and radius r is rotating with angular frequency omega. It suddenly stops rotating and 75% of the kinetic energy is converted to heat. If S is the specific heat of the material in joule per kg Kelvin, the rise in temperature of the sphere is, the moment of inertia of hollow sphere is given as 2 by 3 mr square. The options given are r omega upon 4s, r square omega square upon 4s, r omega upon 2s, and r square omega square upon 2s. Now, the question states that 75% of kinetic energy is converted into heat. So, 75% of kinetic energy of rotation is given as half I omega square, and this is converted into heat. So, from the formula, Q is equals to mc delta T. So this amount of heat is converted into m, which is the mass of the sphere, m into c, or s in this case is the specific heat, and delta T is the change in temperature. So now 75 upon 100 into half, I is given, a moment of inertia is given as 2 by 3, so 2 by 3 mr square into omega square is equals to ms into delta T. So this m gets cancelled, 2 gets cancelled, so what we are left with is 75 upon 100 into 1 by 3 times r square omega square is equals to s times delta T. So now delta T is equals to, this is 25 3s are and 25 4s are, so these also gets cancelled. So finally we are left with delta T is equals to r square omega square upon 4s. Hence option B is the correct answer. Three rods of copper, brass and steel are welded together to form a Y-shaped structure. Area of cross-section of each rod is 4 cm square. End of copper rod is maintained at 100 degrees Celsius, whereas ends of brass and steel are kept at 0 degrees Celsius. Lengths of the copper, brass and steel rods are 46, 13 and 12 cm respectively. The rods are thermally insulated from surroundings except at the ends. Thermal conductivities of copper, brass and steel are 0.92, 0.26 and 0.12 CGS units respectively. The rate of heat flow through the copper rod is, the options given are 1.2 calories per second, 2.4 calories per second, 4.8 calories per second and 6 calories per second. Let's visualize this scenario. There's this copper rod and then this steel and brass rod. So this end is maintained at 100 degrees Celsius, whereas these both ends are maintained at 0 degrees Celsius each. Let this temperature at this junction, let it be at temperature T. Now heat that is flowing through this copper rod is distributed to both steel and brass rods. So therefore what we can say is that Q is equals to Q1 plus Q2. Let Q be the heat that is flowing through the copper rod. So Q1 would be through steel and Q2 would be through brass. So the total heat Q that is flowing can be given by mc delta T. So C times delta T is Q is equals to Ka delta theta upon delta X times T. So using this formula, the K value is given for copper as 0.92 times 4, which is the area of cross section, 100 minus T, that is the junction temperature, upon 46, that is the length of the copper rod. This is equals to 0.26 times 4 into T minus 0 upon 13, this is for brass, plus 0.12 into 4 T minus 0 upon 12, this is for steel. Now as you can see, 46, 92, 13, 26, 12, 12, all these are multiples of each other, and so solving further we get 200 minus 2t is equals to 2t plus t. So therefore T is equals to 40 degrees Celsius. So that junction temperature T is 40 degrees Celsius. So now the total value of Q is 0.92 times 4 into 100 minus 40. So that is 60 upon 46. This value comes around 4.8 calories per second. Hence, option C, 4.8 calories per second, is the right answer. A piece of ice falls from a height h so that it melts completely. Only 1/4 of heat produced is absorbed by the ice, and all energy of ice gets converted into heat during its fall. The value of h is, the latent heat of ice is given as 3.4 into 10 raised to 5 joule per kg, and the value of acceleration due to gravity g is given as 10 newtons per kg. The options given are 136 kilometers, 68 kilometers, 34 kilometers, and 544 kilometers. Now, as this block of ice is falling through a height h, it initially possesses potential energy in the form of mgh at this height. Now when it is falling only 1/4, so for mgh into 1/4, only this amount of heat is being used to change the state, and the amount of energy required to change the state is given by mass into the latent heat. So using this formula, we get mgh upon 4 is equals to m times L. So G is given as 10 into h upon 4 is equals to, latent heat of ice is given as 3.4 into 10 raised to 5. So the value of h comes on 13.6 into 10 raised to 4 meters. So this is nothing but 136 kilometers. Hence option A is the correct answer. Two metallic spheres P and Q of the same surface finish are taken. Weight of P is twice that of Q. Both the spheres are heated to the same temperatures and left in a room to cool by radiation. The ratio of the rate of cooling of P to that of Q is, the options given are 1 is to root 2, root 2 is to 1, 1 is to 2 raised to 1 by 3, and 2 raised to 1 by 3 is to 1. Now, according to the question, mass of sphere P is twice of mass of Q. So therefore, as we know, density is mass upon volume. So writing mass as density into volume. So rho times 4 upon 3 pi radius of P Q is equals to rho times 2 times rho into 4 upon 3 pi r of Q cube. So these rows gets cancelled since it is of the same type, so the density is cancelled, and when we solve this, Rp, we get it as 2 raised to 1 by 3 of R cube. So radius of P is cube root of 2 times R cube. And as we know, the rate of cooling d theta by dt is inversely proportional to R. That is, smaller the sphere, faster would be its cooling. So therefore, rate of cooling for P upon rate of cooling for Q is equals to RQ upon RP. So that is RQ upon RP is given as 1 upon 2 raised to 1 by 3. So the ratio is 1 is to 2 raised to 1 by 3. Hence option C is the correct answer. The rectangular surface area of 8 centimeters cross 4 centimeters of a black body at a temperature of 127 degrees Celsius emits energy at a rate of E per second if the length and breadth of the surface area are each reduced to half of the initial value and the temperature is raised to 327 degrees Celsius. Rate of emission of energy will become, the options given are 3 by 8E, 81 by 16E, 9 by 16E and 81 by 64E. Now the emissive power is given as AE sigma T raised to 4, but since it's a black body, E is 1, sigma is the Stephen's constant, and since the objects or plates are same in both the cases, sigma will be the same. So P is basically proportional to A into T raised to 4. Now as the length and breadth both are half, so the area would become 1/4. So therefore P1 upon P2 is equals to A1 upon A2 times T1 raised to 4 upon T2 raised to 4. So P1 upon P2 is equals to A1 and A2 would be 1/4 of A1. So A1 by 4 times T1 is 127 degrees Celsius. So 127 plus 273 in order to convert into Kelvin raised to 4 upon T2 is given as 327 degrees Celsius. So 327 plus 273 Kelvin raised to 4. So P1 upon P2 is equals to 4 times 127 plus 273 would give 400 upon 327 upon plus 273 is 600, the whole thing raised to 4. Solving this we get P1 upon P2 is equals to 64 upon 81. So therefore P2 is equals to 81 upon 64 times P1. Hence P1, or in this case it is the energy E. So 81 upon 64. Hence option D is the correct answer. Parallel rays of light of intensity I is equals to 912 Weber per meter square, watt per meter square, are incident on spherical black body kept in surrounding of temperature 300 Kelvin. Take Stephen Boltzmann constant sigma is equals to 5.7 into 10 raised to minus 8 watt per meter square per Kelvin raised to 4, and assume that the energy exchange with the surroundings is only through radiation. The final steady state temperature of the black body is close to, the options given are 330 Kelvin, 990 Kelvin, 660 Kelvin and 1550 Kelvin. Now according to this question, suppose this is a sphere of radius say r and parallel rays are incident on it. So the area or the amount of light that is incident on this surface or sphere would be equal to this, would be equal to the cross section or section that is normal to these rays of light. So if we see, we get a circle, and So the projected surface or projected area of this sphere is a circle upon which the rays of light are incident. So therefore the total energy that is incident is 912 times the projected area. So that will be the area of this circle, that is pi r square. So this is the total energy that is incident on the sphere. Now using Stephen Boltzmann's law, so energy or power is equal to sigma A E and t raised to 4 minus t naught raised to 4. Now for black body E is equals to 1. So 912 into pi r square is equals to, the value of sigma is given as 5.7 into 10 raised to minus 8 into the area. Now area of the sphere is 4 pi r square, because the energy incident is on the projected area, but energy emitted by the sphere would be across the whole area. Therefore here we are taking the energy or the area of the entire sphere times t raised to 4 minus t naught raised to 4. So therefore t raised to 4 minus t naught raised to 4 we get as 912 upon 4 times sigma. So 912 upon 4 into 5.7 into 10 raised to minus 8. So this becomes 40 into 10 raised to 8. This is t raised to 4 minus t naught raised to 4. So t raised to 4 is 40 into 10 raised to 8 plus the surrounding temperature is given as 300 Kelvin. So 300 raised to 4. So this is solved as 40 plus 300 raised to 4 is written as 3 raised to 4 into 100 raised to 4. So that we get as 81 and common as 10 raised to 8. Now taking the fourth root, we get around 330 Kelvin, the value of T. Hence option A is the correct answer.